block everything that's.
Well, how come the thing didn't go? Oh, the thing is not connected. Hello?
什么
Hello?
什么时候？
Well, we didn't learn resistance yet. Like,
你的面是什么时候？
how we on static electricity?
All right. How come your back is all wet? So.
He's sweating. Like he wear that like all day.
Take it off.
This attracts sunlight.
Are you serious?
Okay, we're starting the next chapter, double and triple integrals.
Yay.
Okay, let's just review what we did last year. Okay, I'm trying to think of a problem where we can go both directions. Suppose you have, oh, here, right here. Suppose you have the graph of y equal root x and whoop, y equal x over 2. And of course, by inspection, these are the intersection points. How would you find the area of the region bounded by these two curves? What did you do last year?
Length of the curve.
So you can make a rectangle of infinitesimal width. What is the length of this rectangle?
Yeah.
Top minus bottom. That's what you did last year, right? Or do I have to show this picture again? If this is 2 and this is 5, how do I know that's 3? Top minus bottom. That's the height of the rectangle. And what's the width? Dx, right? Delta x, except infinitesimally small. And then you add it all up from 0 to 4. Or you could have made horizontal rectangles, but if you do that, you have to solve for x. So this equation, you would have to go x equals 2y, and this is x equal y squared. What is the length of the rectangle now? Right minus left. Or do I have to show another picture like this? No. Okay, right minus left, that's the height, multiplied by the infinitesimal width, dy, and then you add up all of these rectangles from 0 to 2. Okay, so now we're just going to take a little different approach. Okay, so same region. Whoop. Woo. Now this region is called omega. Because what's going to happen after this is then this would be like the base of a solid or something, but then above it you're going to have another curve above here, and then you got to find the volume of that thing. Okay, so this is the same region, so y equal root x. We have it written over here, we're not going to write it again. So instead of thinking rectangles, now we're going to think of infinitesimally small squares like this. They're infinitesimally small now, so what would this be? Dx, and what would that be? Dy. So we're going to add up an infinite number of little pieces of squares like that. So you have dx dy, and then we're going to do a double integral. So if you do it, here, better do it this way. Let's go with dy dx. So whichever one is here, that's the one you do first. So if you're going to integrate with respect to y first, then what? What do you think? What's the equation of the curve on the bottom? Because you got to go from the bottom one to the top one, right? What's the one on the bottom? Over here. It's x over 2. And what's the equation of the curve on the top? Radical x. Because that's going to be the limit for y. Y goes from here, the bottom, to the top. And then you're going to integrate with respect to x. So what do you think? X is going to go from 0 to 4. This last one on the outside always has to have the constants on it. You cannot, in other words, you cannot like switch it and put the ones with the variable last. The ones with the constants have to go last. See, if you just have a region like this, here, like this. Okay, what if this was 3 and this was 2? Think of the infinitesimally small square there. you do a double integral. If you integrate it with respect to y, y is simply going to go from 0 to 2. And then when you integrate with respect to x, it's going to go from 0 to 3. So y is always from bottom to top, x is going left to right. So you get that? Okay, let's actually compute it now. So the first integral is this one right here. What is the antiderivative of 1 dy? Y. And then you're going to go from, you know what? I'm not going to put the equal sign. Let's just compute this integral separately on the side. Integral from x over 2 to root x of dy. So the antiderivative is y. From x over 2 to root x, plug in the top thingy. Root x, plug in the bottom thingy, x over 2. Okay, so that's what this is. But then now you have to integrate that with respect to x from 0 to 4. But then, isn't that just this? Except you just have that extra step in the beginning. But it's just a different way of thinking about it. And then you're gonna, I know what you're thinking. Oh, why do we have to do that? Why don't you just do it like this? Because this is preparing you for like triple integrals where you're gonna have to do that. All right. So that's, okay, so we could have also done this integral here with respect to y first, x first. So let's do that. So what if you have dx, dy? Okay, so what if you want to integrate from, with respect to x from first, then x is going to go from the left curve to the right curve. And again, you have to solve for x, so this is x equal y squared, x equals 2y. So what would be the limits for x? From the left one to the right one. From y squared to 2y. And then you're going to integrate that with respect to y. So what do you think? Then you got to go from here to here. What is the y value down here? 0. What's the y value up there? 2. And then that would be your double integral to figure out that area right there. And again, why don't we actually compute this? I'm going to get rid of this one here. So you got to do this one first. So what is the antiderivative of 1 dx? What? X. And then we're going to go from y squared to 2y, plug in the top, plug in the bottom, subtract. Okay, so that's what this is. Now we're going to integrate that with respect to y from 0 to 2. But then again, see, look, that's just what this is.
Why can't you use 2 numbers?
Because y is not constant. The only time you're going to have numbers is like, why did I erase the thing? See, like that. Then you can go, okay, I'm going to integrate with respect to y first. So y is going to go from 0 to 2. And then I'm going to integrate from 0 to 3 for dx.
If it's not a rectangle.
Yeah, because, it's not constant. The function changes, that's why.
But why?
So that's why y goes from the bottom to the top. But in this picture, bottom to top is just constant, 0 to 2. This is y equals 0, this is y equal 2.
But you have to have one integral with.
Well, once you pick the one that changes, like over here, if we integrate with respect to y first from here to here, then when you integrate with respect to x, you're only going from 0 to 4.
Oh,
Because you already took care of this one with using the equations of the curve. So that's another thing you got to get used to. All right, so like if you look at the first 6 problems, it's like they're giving you everything, or you don't even need to do it. Look, they're giving you the limits of integration in the problems. Okay, however, when you get to number 3 and 4, I'm going to do a similar problem. I'm not going to do like the same one. Okay, think of, in fact, why don't we just use the same region? Okay, here is omega. We're going to use the same region. The region bounded by y equal root x and y y equal, what did I say, x over 2? This is the 0.42, and of course that's the origin. So this is omega, the Greek, you guys know the Greek letter omega, you guys use that in science.
Yeah.
I don't know what you use it for. Magnetic field? I don't even know. Why am I even guessing? And then now, what if you have like a surface on the top? Somebody give me an equation of a surface, like the one day on your homework is z equals x cubed y. Give me another. Z equal, can we be a little more creative?
Square root.
Okay, how about a paraboloid coming like this then? Like it's a x squared plus y squared?
Yeah.
Okay, we'll try it. I don't know what the integral is going to come out. Maybe it's doable, maybe it's not. Okay, so can you picture so this is the base of the thing. Above it is this paraboloid coming out like this. So we're talking about the region going like this, going up onto the surface, until you hit the surface. So what is the volume between the xy plane and bounded below by this and above by the paraboloid there? Okay, so this is how you gotta think now. See, okay, I'll try drawing a three-dimensional picture. Okay, so in the xy plane, you have y equal root x, and y equal x over 2. That's pretty ugly. And then on the top, you have this paraboloid. So that's a terrible picture. Let me have another try at it. X, y, okay, so, and then above by the paraboloid, here's the z-axis. Like this. So we're talking about the surface. I don't even know where to begin. Who's good at three-dimensional drawing? Okay, can you picture what I'm talking about though?
Yeah.
So how do you figure out the volume of that solid? Oh, this is what you're thinking. We're going to make like these infinitely long, well, not infinitely long, these sticks like this, okay? Infinitely small, what do you call this shape here? French fry? French fry? What else looks like that? Squarish chopstick then? Anyway, so this is dx, this is dy because they're infinitely small, and then that will be z. Right? So what's the volume of that thing? What's the volume of this stick here? Wouldn't it be dx, dy times z? And then what we're going to do is we're going to add up an infinite number of those doing a double integral to cover this omega region here. Okay, so why don't we get the limits? Okay, so if I integrate, I'd rather integrate with respect to y first. Okay, so if I integrate with respect to y, what are the limits going to be? Bottom to top. What's the equation of the one at the bottom? X over 2 to root x. And then you integrate with respect to x, so you're going to go from left to right, which is 0 to 4. See how that last one is constant? Again, you cannot switch it. Can you see why? Because then you're not going to end up with a number as your answer, right? Okay, so this integral will give you the volume of whatever this three-dimensional thing is. So all you have to do now is substitute this thing for z. Let's get rid of this ugly drawing. So you got double integral z, which is x squared plus y squared. We're going to integrate with respect to y first, which goes from x over 2 to root x. Then we're going to integrate with respect to x, which goes from 0 to 4. The hardest part is writing the integral. And then can you see where this is headed? Then we're going to do polar. And then we go to cylindrical and spherical coordinates in 3 dimensions. That's what's going to happen. Do you guys compute centroids and center of gravities in AP Physics C?
Yeah.
Like for irregular regions and things like that? Like, what's the centroid of this region?
It's there.
It's right about here.
Right about.
That's it, just eyeball it. I'm gonna tell Doc that that's what you guys
It's
say.
not even in physics.
Oh, I was just gonna talk to Doc. Hey, you know Jigsaw? Who?
Wait, so if it's like that, if you try to teach an integral, but the integral is an x form, then you need to.
Say that again? You gotta have the numbers on the very left. If you don't,
No, if you solve that.
okay, that's what we're gonna do now. We're gonna solve it. Okay, so you gotta do the inner one first, yeah? Okay, what is the antiderivative of this with respect to y? Antiderivative. That's kind of what you did on yesterday's test. X squared y plus 1/3 y cubed. And then you're gonna go from x over 2 to root x. Right? So fundamental theorem, plug in the top thingy. Plug in root x for y. X to the 5/2 plus 1/3 x to the 3/2. Okay, that's what this is. Oh, no. Now we're gonna do the bottom. Plug in the bottom number. Plug in x over 2 here. X cubed over 2 plus, plug in x over 2 there. X cubed over 24. Is that right? I want to make sure it's right before we go on. Okay, so that's what this is. Now we have to integrate this with respect to x, and we're going to go to 0 to 4, and now you can see how you're going to get a number as your answer, right? Which represents the volume of this thing. So shall we combine this into, make a least common denominator?
13.
This is 13 over 24 x cubed. Okay, so to compute this integral, antiderivative, go. X to the 7/2, 2 sevenths, plus x to the 5/2, 2 15ths, minus x to the 4, 13 over 96, from 0 to 4. Plug in the top number. Song, redeem yourself.
Oh.
Easy, that's easy. I'll do the denominator.
Wait. Oh, wait.
You do the first term.
256.
Very good. Okay, the next term, learner. Wait, let me do the denominator for you.
That's 64.
Yes.
Yeah, 64.
Job 64. And then Hong, I'll do the 96. Oh, that's easy, yeah?
Can you reduce it?
13 over 96?
No, I can't.
Oh, yeah, after, but then I want you to plug in the 4. Come on, just square it twice.
256
Yeah.
is 13.
And then minus 0 plus 0, so,
Times
Times
13.
13.
yeah, that's what I meant. Times 13. And then, of course, you simplify it, yeah. Anyway, once you get here, the most you can lose is 1 point.
Oh.
But I still expect you to simplify it. There's still some people in the period 9 class, they think this is AP test where you can leave your answer like that. Well, you can, but you're gonna get minus points for not simplifying.
Wait, it's 1
Can
point.
you leave it? Just 1 point?
No, if this was the AP exam, you can leave it like that. Are we taking an AP exam?
No, but for the twice
Wait, it's just 1 point, right?
Yeah, 1 point.
Oh, okay.
What are you talking about?
Just take 1
No,
point.
just no, we're just wondering, If it's one, we're just making it,
If it's a number.
yeah.
But if there's like variables and thing, that's something else. That's algebra now. This is arithmetic. You see the difference between the two? Okay, so the whatever. We're done. Done. Okay, so you guys are gonna make corrections. Oh, let me turn off this video. Okay, look, I even put the answers on the board. Wait, let me turn